This is an item analysis of the 20 questions that were on the exam, and I'm going to sort by average score. And these 5 problems here have the lowest average score. Obviously, I did not do a good job talking about quantitative, qualitative, sampling methods, and then the 2 givens, the problem 13, well, I don't remember it was problem 13 or 20. One of these, you actually got the first 2 parts correct, and then the second 2 parts fell apart. So let's just take a quick look. Quantitative, qualitative. So the key here was to look whether or not you were counting, measuring, or was it an attribute? So you're collecting age in years. Well, that's questionable. It's a number, so I would go with quantitative. That one's a little bit tricky for me. Did anybody have that one, age? Did you? Did you get it right? I'll go back and look.
There was one other one that was just
You collect a wage per hour. That's obviously quantitative. Number of traffic. Well, number, that's not even a question. That is quantitative. But you can see, so this one, happy, that's qualitative. So you can see it, usually in this particular question, they would give you a number, or they'd tell you that they'd have the word number in there, or they're measuring something that's quantitative. So if you count it, which is what we're going to do today, we're going to talk about discrete random variables. If you count it, it's discrete quantitative data. If you measure it, it's continuous quantitative data. All right. Then, and unfortunately on these multiple choice, I can't get partial credit. Sampling method. In a study, the sample is chosen by dividing the population by voting precinct and sampling everyone. So what is that? Cluster. If you sample everybody, it's clustered. If you take a sample from each group, that's stratified. So it's just divided by precinct, sampling everyone, that's cluster again, isn't it? Same question. Studies chosen by pulling 50 names from a hat. That is simple random. So I think the one that got missed was the stratified. Somebody had stratified or systematic. Let's see if we can get one of those. What's the started choosing every 5th person? If it's every 5th person, every thing, that's systematic. It's stratified again if you break it up into groups and then you sample from each group. Okay. So this one, the online class had the same issue. If it's a given, that reduces the sample space to only those that have that attribute. So if we're looking at students who were male, given that they got a B, then you're only going to look at the number of Bs that were awarded. So how many Bs were there? 27? And how many of those were male? 19? So 19 of the 27 got a B given they were male. Oh, I can't read. Oh gosh, 51 were male. Let's probably say, oh wait, they were male given they got a B. Okay, I was right the first time. It's 19 over 27, because we're interested in the people who got Bs, and of those people who got Bs, how many of them were male? So is that 19 over 27? So in the case of a conditional probability, whatever the given is, given that they got a B, that reduces the sample space to just that number, the number of people who got Bs. Okay? And then marbles from a bag and not independent. Suppose a jar contains trying to make the window bigger. There we go. Suppose a jar contains 10 red marbles and 19 blue marbles. If you reach in the jar and pull out 2 marbles at random at the same time, find the probability that both are red. So what's the probability the first one's red? Are there 10 out of the 29 that are red? What's the probability the second one's red? 9 out of 28. And it's an and probability. This one's red and that one's red. They're both red, both meaning and. So it's a multiplication, isn't it? So you take the 10 over 29 and multiply that by 9 over 28. Okay, and what's the next one? So this is the one, the first 2 parts you were fine and dandy with. The second 2 parts, not so much. The marble is red. So how many marbles do we have in this particular example? We have 22 red and 52 blue. Is that 74 marbles? 22 of which are red. So is that 22 over 74? Is that 11 over, what's 74? 37? Okay, and then how many are even or odd or doesn't matter? Half of them? Okay, and then in the next 2 parts, you actually have to use the addition rule because you're looking for, is it red or is it odd? Okay, so you have to add the probability that it's red to the probability that it's odd, and then you have to subtract off all of those that are red and odd. And how many are red and odd? 11? So you have to subtract off, you have to add the 11 over 37 to the 1/2, and then you have to subtract off the 11 over 74. And the same is true for the next one. How many are blue? Well, the 52 out of 74. How many are even? Half. How many are blue and even? 26 out of the 74. So when you have that it can happen at the same time and you're finding an or probability, you have to add them up and subtract off. They can be the same thing. So it's the Venn diagram. So you got a Venn diagram where you got the 2 circles and you have to subtract off the overlap because the or is both circles combined. And if you don't subtract off the middle, you add it twice. So you have to subtract. All right, any questions on that? Said I got no complaints. The average was 82. What have I got to complain about? All right. We are going to start discrete probability distributions today. And I thought we might real quick take a look at some Excel. Bless you. So day before yesterday, someday this week, I decided to do an experiment. And the experiment I decided to do was rolling a die, a 6-sided die. And so as we did early in the semester, I created a random number generator in Excel that generated numbers between 1 and 6. So to simulate the experiment of actually rolling a fair 6-sided die. And I did it 2,000 times. So I created 2,000 random numbers. And how difficult is that to do in Excel? It's not difficult at all, because you can just put in the rand between and then just pull it down in whatever column you put it in to as many as you want. So you can generate, thousands and thousands of these in seconds. So then I created a pivot table to count the number of ones, the number of twos, the number of threes, the number of fours, the number of fives, and the number of sixes that my random number generator generated. And this is a frequency table, because I have the values that my die can take on. So what value, when I roll a die, can I get? And then in my 2,000 simulated rolls over here, this is the number of ones I got, the number of twos, the number of threes, etc. So that is a frequency table. So to create a relative frequency table, I took the count and I divided it by the total. So I took the 312 and divided by 2,000, and that gave me a relative frequency. It's also the probability that I get a 1. So if I get 312 ones out of 2,000 rolls, then the probability that I get a 1 from this experiment is 0.156. So the relative frequency can be equated to a probability. And that makes sense, correct? Because simple probability is the number of outcomes you get that favor the event divided by the total number of outcomes. Since I did this 2,000 times, and the number of outcomes that favored a 1 were 312, I take the 312 and divide it by 2,000. And I did that for all of them. And then I created a bar chart from the relative frequencies. So this bar chart is from this data here. And it looks pretty much like I would expect it to look. I would expect this to be uniform. I would expect that it's relatively flat. I wouldn't expect a bell shape at all. That's for sure. And I want you to notice something down here. Down here at the bottom of my Excel spreadsheet, I actually have some things programmed into my Excel that it will find the average. Oh, that might come in handy later, by the way. Finds the average, it finds the count, but it also finds the sum of those relative frequencies. And what's the sum? And is that important? So this is a probability distribution. This probability right here is the probability. That's a relative frequency. That's a frequency table. This relative frequency table is a probability distribution, because it shows what my outcomes are, and it shows the probability that I get that outcome. And that's what a probability distribution does. Okay. So let's go to our PowerPoint. So the title of this chapter is Discrete Random Variables. And from these discrete random variables, we are going to get probability distributions. And we're going to look at several different probability distributions. But these probability distributions deal with discrete data. So they deal with data that you count. And a frequency table is a count, correct? So the experiment that I ran, rolling a die 2,000 times, I used a pivot table to count the number of ones, twos, threes, fours, fives, and sixes I got. So this deals with data that I count. Okay, so we're going to first recognize and understand what discrete probability distribution functions are in general. Then we're going to calculate and interpret expected values. Your calculator can do this, as can Excel. Did you see that average that we got there? That's the expected value. So your calculator can do this. Recognize the binomial. So the first discrete probability distribution we look at, other than the general ones like rolling the die, is the binomial distribution. You can do that on your calculator. And the reason, isn't it nice that someone came up with formulas for the binomial distribution, which we'll discuss later? Because I was making a tree diagram the other day to demonstrate a problem we're going to look at, guessing the answers to a true false test. And of course, it gets so complicated so quick, you got to quit. And so, isn't it nice that someone came up with the binomial distribution that will find probabilities of something either being good or bad, or correct or not correct, etc. Then we're going to look at the Poisson distribution. And does anyone speak French? I always get his name, I'm sure, butchered. He's a French mathematician. Poisson, I think is the way it's pronounced. And then we'll talk about the geometric distribution and the hypergeometric. And the hypergeometric is not a distribution that's included in the TI 83 or 84 calculator. It can be done in Excel quite easily. It's also very easy to do by formula. So all the problems that you have using the hypergeometric distribution will not require you to find cumulative distributions. It only requires you to find the probability of a single event happening, which is quite easy to find. So it's a pretty easy distribution. Either use a formula or use Excel. It's the only one that we do the entire semester that is not included in your calculator. Okay, so here are some examples of where you might use a discrete probability distribution. A student takes a 10-question true-false test. Because the student had such a busy schedule, he or she could not study and guesses randomly at each answer. What's the probability that the student will pass the test with at least a 70%? So a 70% or higher. To actually calculate that is quite cumbersome. So isn't it nice that somebody came up with a formula for us that will calculate this? Isn't it nice that someone programmed your calculator to calculate that? Small companies might be interested in the number of long-distance phone calls their employees make during the peak time of the day. Suppose the average is 20 calls. What is the probability that the employees make more than 20 long-distance phone calls during the peak time? These are two examples that illustrate two different types of probability problems involving discrete random variables. Again, discrete because you're going to count the number that you got correct to see if you made a 70%, or you're going to count the number of long distance calls that are made. Recall that discrete data are data that you count. A random variable describes the outcome of a statistical experiment in words. The values of a random variable can vary with each repetition of an experiment. So here's your definition of a random variable. Well, it's the notation we use and the description down at the bottom. A random variable describes the outcome of a statistical experiment in words. We use capital variables for random variables. So capital X or capital Y, capital A, capital B, whatever. And then we use lowercase letters just to confuse you to describe the values that your random variable can take on. And if X, capital X is a random variable, then little x, capital X is written in words and little x takes on a numerical value. So for example, let's let capital X, the description of my random variable, be the number of heads you get when you toss 3 fair coins. So what's the sample space when you toss 3 fair coins? Well, the sample space would be, you could get all tails, or you could get the first one as a tail, the other 2 as heads, or you could get 2 of them are heads and one of them is a tail. And you get that in head, tail, head, or head, head, tail. You could get the first one's a head and the other 2 are tails. You could get the first one's a tail, the second one's a head, and the third one's a tail. You could get the first 2 are tails, and the last one is a head, or all 3 of them could be heads. Okay, so that's the entire sample space of this experiment. And you could find this sample space by doing a tree diagram. If you didn't get it just by looking at it, you could certainly do a tree diagram. So you could say something like, on the first coin, I could get a head or a tail. And each of the second, I could get a head or a tail, head or a tail. And then each one of those, I could get a head or a tail, a head or a tail, head, tail, head, tail. So you could find the sample space. It's a pretty small sample space, fairly easy to find using a tree diagram. Okay, so if X, the random variable, is the number of heads you get when you toss 3 fair coins, what numerical values can X take on? So little x. So little x could be that if you've tossed 3 fair coins, you don't get any heads. So when you get the result of your experiment to be tail, 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 there are no heads there. So X could be the value 0. What other value can X take on? Well, you could toss 3 fair coins and just get 1 head, correct? So it could be a 1. You could toss 3 fair coins and get 2 heads. So it could be a 2, or you could toss 3 fair coins and all of them be heads. So the random variable is the number of heads you get when you toss 3 fair coins. The value that your random variable takes on would be 0, 1, 2, or 3. X, capital X is in words and little x is a number. And yes, capital X and little x are 2 different variables. They are not the same variable. Notice that for this example, the X values are countable outcomes. That's what makes this data discrete. Because you can count the possible values that capital X can take on, and the outcomes are random. The X values are 0, 1, 2, or 3. X is a discrete random variable. Okay, so let's talk about discrete probability distributions. A discrete probability distribution function has 2 characteristics. Each probability is between 0 and 1, inclusive. So you could have probabilities that are 0. You could have probabilities that are 1. And then the sum of the probabilities is 1. So when we looked at the Excel spreadsheet and I showed you that the sum of the probabilities was the number 1, then is that a discrete probability distribution? And the answer is yes, because each of those probabilities the number of ones, the number of twos, the number of threes, etc., divided by the total number of outcomes in my sample space, 2000, each one of those probabilities was between 0 and 1. All right. A child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. So we're going to let the random variable, capital X, be the number of times per week a newborn baby's crying wakes its mother after midnight. And for this particular example, the discrete values they got were between 0 and 5. So 0 meaning that the baby didn't wake its mother up at all, and 5 meaning that the baby woke its mother up after midnight 5 times. Okay, so this is a frequency table. And in this frequency table, we see the values that our random variable can take on. So these are the values of our random variable. And then the frequency. And so from that, we can create a probability distribution. So if I take each one of these frequencies, what was the total? They surveyed 50 mothers. So the total is 50, correct? So if I take each one of these frequencies and I divide it by the total, then I get the relative frequency or the probability. And the way we write that is P of X, the probability that in this experiment, my random variable takes on that value. So this first one is P of 0. The second one is P of 1. The third is P of 2, etc. So that is the probability that my random variable can take on that particular value. So from this, I can create my probability distribution. And there it is on the lower left. So the probability that X takes on the value of 0 is 2 out of 50. The probability that X takes on the value of 1 is 11 out of 50, 2, 23 out of 50, etc. Now, what has to be true for this to be a discrete probability distribution is that each of those probabilities on the right side of that table in the second column have to be between 0 and 1. They all are. And that the probabilities must add up to 1. And those probabilities do add up to 50 over 50 or 1. So this is a discrete probability distribution. And should kind of sort of make sense that it's a discrete probability distribution because we created it from a frequency table. So it should be, if we create it from a frequency table, finding the probabilities by finding the relative frequency, then it's going to be a discrete probability distribution. A hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. So the random variable, capital X, is the number of times a patient rings the nurse during a 12-hour shift. And for this experiment, that random variable took on the values from 0 to 5. The probability of X is the probability that the random variable takes on a value of 0, 1, 2, 3, 4, or 5. So why is this a discrete probability distribution? So we have in the first column of our table, the values that our discrete random variable can take on. And then in the second table, we have, second column, we have the probability. And that is the frequency of that value divided by the total surveyed. So 4 patients rang the nurse no times. 8 rang it once, and etc. So do those probabilities add up to 1? Well, for it to be a discrete probability distribution, they do have to add up to 1, and each probability has to be between 0 and 1 inclusive. So this is a discrete probability distribution. And you have a problem in your homework that asks this. Is this a discrete probability distribution? And that's what you have to look at. Are all the probabilities between 0 and 1 inclusive? And does the probability column add up to 1? Okay, suppose Nancy has classes 3 days a week. She attends classes 3 days a week, 80% of the time. 2 days, 15% of the time, and 1 day, 4% of the time, and no days, 1% of the time. Whoa. Suppose 1 week is randomly selected. Create a discrete probability distribution. So what is your capital X? What is your random variable? So the number of days in class? And what values do these random variables take on? So 0 through 3? She's either in class no days, 1 day, 2 days, or 3 days, in a attending 3 day a week. Okay, so what's my distribution look like? So over here in the first column, I'm going to write the values that my discrete random variable can take on, 0, 1, 2, and 3. And in the second column, I'm going to write the probabilities, which they already gave me, did they not? Since they gave me this information in percentages, they have already calculated the relative frequency for me. So since it's a percentage, that is the probability. So no days, was that 1%? So is that 0.01? And we do write these as decimals. We don't normally write probabilities. Well, in a discrete probability distribution, your probabilities should be decimals. I'll put it that way. So what was the 1? 4%? And 2, was that 15? And 3, was that 80%? Does that add up to 1? Yep. So that is the discrete probability distribution that describes Nancy's class habits. All right. Calculating the mean and expected value and the standard deviation from a probability distribution. I do this once by hand, and then we let the calculator take over. There's your calculator, will do this. Your calculator will find the mean of a frequency table. I'll have to go back and look at your problem where you had to find the mean of a frequency table. I think you guys all did that correct because you sat in class and watched me do it on the calculator. The online class, not so much because they tried to do it by hand. We're going to let the calculator do it. All right, the expected value is often referred to as the long-term average or mean. This means that over the long term of doing an experiment over and over, you would expect this average. You toss a coin and record the result. What's the probability that the result is heads? If you flip a coin 2 times, does the probability tell you that these flips will result in 1 head and 1 tail? You might toss a fair coin 10 times and record 9 heads. Probability does not describe the short-term results of an experiment. It gives information about what can be expected in the long term. To demonstrate this, Carl Pearson once tossed a fair coin 24,000 times. That's dedication. He recorded the results of each toss, obtaining heads 12,012 times. In his experiment, Pearson illustrated the law of large numbers. So let's go back to my experiment that I conducted earlier this week in my Excel spreadsheet. So this is the results of my experiment, but it's not equal to the theoretical probability. It approaches it, but is not exactly equal to. So what would the theoretical probability be? 1/6? What's 1/6? I think it's 0.166 if I remember correctly. 1.6666. So theoretically, the probability of getting a 1, 2, 3, 4, 5, or 6, each of those should be 0.1667, 1/6. But because I'm conducting an experiment, I'm not getting exact results. But if I did this 10,000 times or 20,000 times, I would see that the relative frequency would get closer to the 0.1667. I'm pretty good here anyway, not too bad. Okay, so the law of large numbers says that as the number of trials in a probability experiment increases, the difference between the theoretical probability of an event and the relative frequency approaches 0. The theoretical probability and the relative frequency get closer and closer together. When evaluating the long-term results of statistical experiments, we often want to know the average outcome. The long-term average is known as the mean or expected value of the experiment, and we use the Greek letter mu to describe that. So this is the Greek letter mu. So does anybody do Pokemon? Is there a mu in Pokemon? I think so. So it's the Greek letter mu, and it's a U with a tail in the front. So the way I make it is I start down here, if my pen will write. I start down here and then I make a U, and that makes a mu for me. In other words, after conducting many trials of an experiment, you would expect this average value. So the formula for the expected value or long-term average mu, simply multiply each value of the random variable by its probability and add the products. So to find the expected value by hand, you take the probability table, multiply the value of the random variable times the probability, and then add those up. To find the standard deviation, we're going to give up pretty quick and let the calculator do this. You have to take the difference in the value of the random variable and the mean. So each random variable, you're going to subtract the mean from that. You're going to square that, multiply it by the probability, and then take the square root. So that gets cumbersome really quick. So we're going to let the calculator do it. All right, so let's do it once and then we'll say we did it and then we'll go let the calculator do it. A men's soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5. And the probability that they play 2 days is 0.3. Find the long-term average or expected value mu of the number of days per week the men's soccer team plays soccer. To find the expected value or long-term average, mu, simply multiply each value of the random variable by its probability and add the products. Okay, so what's our random variable? So a random variable, capital X, is what? The number of days per week that they play soccer. Can I spell soccer? Nope. So what does values do our random variable take on? What, 0 through 3? Is that correct? 0, 1, or 2. 0, 1, 2, not 3. Okay, so I'm going to go set up a probability distribution for this. My random variable can be 0, 1, or 2, and we have the probabilities, correct? So let's go set that up. 0, 1, and 2. And the probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5. And the probability they play 2 days is 0.3. Okay, so now we're going to take each of these random variables, values, and we're going to multiply it by the probability. So we have 0 times 0.2 is 0. We're going to take 1 times 0.5. That is 0.5. Maybe I should use parentheses. That'll be a little bit clearer. We're going to take 2 times 0.3. And that's going to be what? 0.6. And you add that up. And you get mu. So the expected value of this discrete probability distribution is 1.1. So on average, they play 1.1 days a week. So in the long term, some weeks they play 2 days a week. Some weeks they don't play at all. So over the long term, on average, they play 1.1 days a week. Now, there is no week that they play exactly 1.1 days. This is a discrete probability distribution. That doesn't make any sense. We need the values that our variable take on to be countable quantities. But on average, over the long haul, they play 1.1 days per week. Okay, now calculating the standard deviation. So I found the average, the expected value of this distribution to be 1.1. So I go into my distribution and I take the value of each of my random variables and I subtract mu from that. So I take 0 and I subtract 1.1. I take 1 and I subtract 1.1. I take 2 and I subtract 1.1. Then I take that value and I square it. That's the next column in the table. Then I have the probabilities of each of those random variables, of each value of the random variable, and I multiply that difference times the probability, and I add it up. And I get, what do I get? Wait, 0.49? Oh, that is the sum. Duh, Lisa. It helps if you look at your, okay, and then you take the square root of it. So sigma is the square root of 0.49 or 0.7. So the long-term average is 1.1 with a standard deviation of 0.7. All right, let's haul out our calculator, shall we? Have you got your calculator with you? Now, it's been a few days since I've used my calculator, so I don't know exactly what I have in my lists. So I'm just going to clear them all out. So I'm going to go second plus, and I'm going to clear all my lists. Number 4. Okay, so now I'm going to put that discrete probability distribution in a list, 2 lists, because it's a table. So I'm going to go to Stat, Edit, and I'm going to put in my first list the values of my random variable. So what did we have? 0, 1, and 2. And then in the second list, I'm going to put the probabilities. So what were our probabilities? 0.2, 0.5, and 0.3. Okay, so once I have that data in, so the values of my discrete random variable would be in the first list. The probabilities would be in the second list. I'm going to get out of here, and I'm going to go to my Stat menu, to the Calculate menu, which is going to arrow to the right to get there. And I'm going to calculate the one variable statistics on that data. So I put my random variable information, the value of my random variable, in L1. And my frequency is my probability. That is my relative frequency. So that's going to be the probability. And I put that in L2. While I'll be, same answer. So mu in this case is written as X bar, but that is mu, the average of that discrete probability distribution. And then sigma, you notice there's no S, it doesn't calculate that. So sigma, the standard deviation is 0.7. So I don't know about you, but I'd let my calculator do it. All right. I say that, and then we're going to calculate. You're playing a game of chance in which 4 cards are drawn from a standard deck of 52. You guess the suit of each card before it is drawn. The cards are replaced in the deck on each draw. So this is a with replacement experiment. You pay $1 to play. If you guess the correct suit every time, you get your money back and $256. What is your expected profit of playing the game over the long term? So we're looking at a discrete probability distribution where our random variable is what? What are we interested in? The profit? Yeah, the amount of money you make. So we're interested in the amount of money you make, the amount you profit. Okay, and then what values can little x take on? So you're going to either lose a buck or you can make 256. So if I lose a buck. If I win, I get my $1 back. So now I'm neutral and I get $256 to boot. So I get my $1 back and then I make 256. So I can either lose a buck or make 256. So what's the probability of losing? So what's the probability that I get X is -1? Well, how about this? What's the probability of winning? Okay, so if I guess them correctly, so I guess the first one correctly, the second one correctly, the third one correctly, and the fourth one correctly, it'd be 1/4 times 1/4 times 1/4 times 1/4. Did I do that 4 times? So is that 1/256? So what's probability of losing? If winning is 1/256, losing is 255/256. Okay, so in the slides, they get decimal approximations to this. So the probability of losing is 0.9961, and the probability of winning is 0.0039. Okay, so from this, I can create a probability distribution table and either let my calculator, it's pretty simple to do, or just calculate the expected value. Okay, so there's our little probability distribution. So we're going to take X times P of X. So this is going to be negative 0.9961, 256 times 0.0039. Did I do that on my slides? I did not. Why didn't I do that on my slides? I didn't know. .9984. So the expected value mu is the sum of those two values. And so mu is what? 0.0023. So the long-term average, that is in dollars. That is dollars. So is it 0.23 cents? Because if I convert from dollars to cents, I multiply by 100 per $1. There's 100 cents. So if I multiply that by 100, I get the long-term average is 0.23 cents. So if you play this game repeatedly, on average, you're going to lose less, you're going to win less than a penny. You are going to win, but it's less than a penny. So games of chance. If you play games of chance, you either win or you lose. Correct? I mean, if I go to the slots and put a quarter in the slots and hit the button, it's either going to win or it's going to lose. But the long-term average value you get from playing slots, you can calculate this way. And they actually put the probability of winning somewhere on the machine. It should be on there somewhere. So you could figure out what your long-term expected value from playing. And these are games of pure chance like this. Pure chance. Doesn't take any skill to guess the suits. All right. Now I had a friend when I worked at Seagate. Her husband would walk in and play slots and walk out with the IRS following him. So I don't know what his long-term average was. I always wondered what it was, because twice he had to go see the IRS guy before he left the casino. All right. This is a homework example from homework. And I always get a multitude of questions on this. So I have a pad example that I send to the online class. So when someone asks me about question 4 on the first homework in this chapter, I say, here's an example. A jar contains 6 pennies, 5 nickels, and 5 dimes. A child selects 2 coins at random without replacement from the jar. Let X represent the amount in cents of the selected coins. Find the probability that the kid gets 10 cents. Find the probability that the kid gets 11 cents. And then find the expected value. So if I have to find the expected value, I have to find out all the different values this kid can get. So if I have a nickel, a dime, and a penny in a jar, what are all the different values of those 2 coins can this experiment result in? So being me, I created a tree diagram. So if I draw 3 coins out of a jar that contains a penny, nickel, and a dime, can I get a penny, a nickel, and a dime? Okay, so what happens in the second draw? Can I get a penny, a nickel, and a dime? Can I get a penny, a nickel, and a dime? Can I get a penny, a nickel, and a dime? Okay, so what's your sample space consist of? I should probably just make that an S. So I could get 2 pennies, correct? Correct? Could I get a penny and a nickel? Could I get a penny and a dime? Could I get a nickel and a penny? Could I get a nickel and a nickel? Could I get a nickel and a dime? Could I get a dime and a penny? Could I get a dime and a nickel? Could I get 2 dimes? So you told me what values my random variable can take on. So what values can my random variable take on? Well, I could get 2 cents, correct? I could get a penny and a nickel. Is that 15? Okay, but the next one would be penny and a nickel, 6, Lisa. So I could also get what? A penny and a dime, is that 11? A nickel and a penny, that's 6. I've already got that written down. 2 nickels, is that 10? So let's put the 10 there and the 11 there. And a nickel and a dime is 15, is that correct? And then we got penny, a dime, penny, which is 11, I got that down. Dime, nickel, is that 15? I got that down. And 2 dimes? So are those the values X can take on? And then you got to calculate them. And this is like, and this is on your test. So this is the hardest part of this problem. And it's really not that difficult because you know how to find probabilities. So you know how to find the probability that I get a penny and I get a penny without replacement. So what's my distribution look like? Well, I can get what? 2, 6, 10, 11, 15, and 20. Okay, so what's the probability that I get 2 cents? Well, how many nickels, dimes, and pennies do I have? Do I have 16 coins total? And how many of those are pennies? 6? So is the probability of getting 2 cents, is that 6 out of 16? Times what? 5 out of 15? Now, what's the probability of me getting 6? So the probability of me getting 6 would be a penny nickel or a nickel penny. Did you hear that or? Or. So what are you going to do? You're going to add the probabilities together. So what's the probability of getting a penny and then a nickel? Well, what do I have? Pennies, do I have 6 pennies? And what about nickels? Do I have 5 nickels? And then add that to that, what's the probability of getting a nickel? Is that 5 out of 16 times what? 6 out of 15? And you can calculate those for the rest of them. Now, the two questions getting 10, what's the probability of getting 10? Nickel, nickel? So what's a nickel, nickel? So in my case, is that 5 out of 16 times what? 4 out of 15? So I got that one. What's the probability of getting 11? Well, getting 11 is what? Penny, dime, or dime, penny? So I've got to add two probabilities together. So what's the probability of getting a penny then a dime? Is that 6 out of 16? And what is a dime? 5 out of 15 plus 5 out of 16 times 6 out of 15. And you continue in that manner. So then once you get the probabilities, all these probabilities, you can find the expected value. So you can put this in a list and this in a list and calculate them up. Okay, are you really listening to me? Everybody awake? What did we have? 2, 6, 10, 11, 15, and 20. Is that correct? Okay. Can your calculator calculate this for you? So what did we have for 2? Did we have 6 over 16 times 5 over 15? So is that 6 times 5 divided by 16 times 15? So down here, can I take 6 times 5 divided by, what are we dividing by? Now I could just do it straight across, but 16 times 15? Sweet. So is it going to be in there when I'm ready to go? So what was the next one? It ended up being 2 times, because it's 6 over 16 times 5 over 15 plus 5 over 16 times 6 over 15. So it ends up being 2 times whatever that was. So I can go 2 times, then I have 30 divided by, and what are we dividing it by? 16 times 15? And I need to close those parentheses twice. And then once you get all these done, then I can run one variable statistics on those two lists and get my expected value. Okay. If you have any questions on that when you start working on it, let me know. Here's another one from your homework that I get frequent questions on. And I don't know why. As a matter of fact, I was describing this problem to my husband the other day. Now, granted, my husband, when he was at Seagate, specialized in Six Sigma. He was a Six Sigma black belt, which is a big dang deal. So he's very schooled in statistics. His master's, I used to have it written down somewhere, so I'd always remember his title. His master's is in like operational research or something, very statistics stuff. So when I talk statistics to him, he usually knows what I'm talking about. So I was describing this one, and he goes, well, wouldn't you just? I said, yes, dear, you would. Data were collected from a survey given to graduating college seniors on the number of times they changed their majors. Sound familiar? I never changed mine. I wanted to, but I didn't. From that data, a probability distribution was constructed, and it's a sideways table, but that doesn't make any difference. If it bothers you, put the X in a column and put the P of X in another column. And you don't need your calculator except to be adding on this one, because I don't think you need to find an expected value. The random variable capital X is defined as the number of times a graduating senior changed majors. And then the values that your random variable takes on are any numbers between 0 and 8. What's the probability that a randomly selected student changed his or her major at least once? What's that mean? What's at least mean? Not more than once, but one or more. Okay, and that's a kind of a, you're saying nitpicky caveat there, maybe, but it does make a difference. To say more than one means two or more. At least one means one or more. Okay, so how could you do this? How would you find the probability that you change majors at least once?
Well, if they all add up to one, you just subtract the 0, but if they don't all add up to one, you have to add them.
Well, they have to add up to one,
So,
because this is a discrete probability distribution. So they have to add up to one. So did you hear what he said? At least once would be 1 minus the probability that you don't change it at all. So at least once, you can add up, you certainly can, you can add P of 1 and P of 2 plus P of 3 plus dot, dot, dot plus P of 8, correct? You could add those all up. Or at least once X is greater than or equal to 1, at least once, would that be 1 minus the probability of 0? Why, yes, it would. Whatever that is. Okay, then what about the next one? What's the probability that a randomly selected student changed his or her major at most twice?
add everything under 2.
And 2. So this would be, we're doing the problem for you, correct? At most 2, no more than 2, 2 or less. What's the probability that a randomly selected student changed his or her? Oh, I do have to find the mean, by the way. So we are going to use our calculator. What is the probability that a randomly selected student changed his or her major 2 or more times? So you could do this one of 2 ways. You could add them all up, correct? 2 or more. And you have a calculator. So this is not a significantly difficult addition to do. But 2 or more, if the total probability is equal to 1, could you subtract off from 1 the sum of 0 and 1? And that's one way you can check to see if you did it right. So this should equal 1 minus the probability of 0 plus the probability of 1. Put that in brackets. So they should be the same thing. Okay, find the mean. So I'm going to put this in my calculator. I'm going to put that in L1 maybe. And this in L2. So put the X's in the first list and the probabilities in the second list, find the mean. That'll give you the mean and standard deviation when you run the one variable statistics. And then the last one's a bonus. So I don't know if I want to tell you how to do it. Maybe I will. If a student changes their major at least once, what is the probability that they change it more than once? What's more than once mean? Greater than 1? Did you find greater than 1? So 2 or more and greater than 1 are the same thing. In a discrete probability distribution, greater than 1 means not equal to 1. Greater than 1 would be 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. So 2 or more and greater than 1 are the same thing. Okay, so if I'm interested in a student changes his major at least once, what's the probability that they change it more than once? So if I'm only looking at those people who change their major once, at least once, that is this, correct? So now I'm reducing the sample space, the probability, to just those people who change their major at least once. So if I take part C and divide it by part A, should that give it to me? Hopefully. So now you're only looking at the people who changed it at least once, that group of people. And then what's the probability they changed it more than once? And that's all I'm going to do today because I only have 3 minutes left anywho. Are there any questions? This first homework's pretty straightforward, but I did the 2 hard problems with you. So hopefully that'll go okay for you. All right. If there's no questions, we'll see you next Tuesday.